Okay, so next we're going to be talking about what's called inverse reinforcement learning. Okay, the motivation here is where does this reward function that we've been talking all about come from? So in many domains, so reinforcement learning has been very successful in domains like computer games. And you've seen a lot of kind of simulations in computer games so far. In computer games, it's actually very clear what the reward function is going to be. It's the score. It can be, and your goal is to maximize your expected score at the game. And the game just gives you this nice reward function and feedback for how to improve and how to get better. But in many real-world scenarios, it's much less clear. So say you want your robot to be able to pour a cup of water using a pitcher just like this child here. Or maybe you're interested in dialogue and you want to be able to talk to another agent. You want your agent to be able to talk to you. Or maybe you're interested in autonomous driving. In all these scenarios, the real world doesn't just give you a reward function for how well you're doing. In many cases, we'll often use a proxy for the true reward function. Maybe we'll design a detector for liquid and measure if the liquid spilled, how much of the liquid spilled, how much of the liquid made it in the cup. But going through that engineering process seems a bit silly if our goal is just to pour water, and may even be more complicated than the behavior itself. And likewise, in dialogue and autonomous driving, we have ways that we can try to measure how well we're doing, but aren't actually the true reward function. And in many scenarios, it's actually easier to provide expert data for how to do a task rather than providing a reward function. And so the approach that I'm going to be talking about in this lecture is the ability to infer a reward function from rollouts, from trajectories taken from an expert policy. Okay, so if we're going to assume trajectories of the behavior that we want, like example trajectory of pouring water, why do we want to infer the reward function? There's an approach called behavioral cloning. It goes by other names like direct imitation learning. And in this approach, you typically just mimic the actions of the expert that you observed. This approach is quite simple. In many cases, it actually can work quite well. But there's a couple drawbacks. The first is that there's no reasoning about outcomes or dynamics and how the goal of what you're trying to achieve. And also, the expert might have different degrees of freedom than the agent. And they might try to perform a goal in a different way than the agent is trying to perform it. So instead, can we reason about what the expert is trying to achieve, and then do that ourselves, to try to achieve what the expert was trying to achieve. And interestingly, this is something that humans can do at a pretty young age. So this is a video from experiments in cognitive science, and here an adult performed a task, actually failed to perform a task. And without any instruction, the infant here, the young child, will infer what the adult was trying to do and help the adult. So it's clear that humans have the ability to imitate from a very young age, but they also have the ability to infer what others are trying to accomplish and then figure out how to accomplish that themselves. Yes? It's possible. I think that generally when you infer goals, you come with a lot of prior experience. So you're not trying to generally infer it from scratch. Okay. So this is known as the problem of inverse reinforcement learning or inverse optimal control. The goal is to infer the reward function given a set of demonstrations. More concretely, the input to the system is going to be some state and action space, rollouts from the expert policy, and sometimes a dynamics model. And then the goal is going to be to recover the reward function underlying the expert demonstrations, basically recover the reward function that the expert was acting under, and then use that reward function to get a policy. Okay, so why is this a hard problem? First, it's actually an underdefined problem. There's many different reward functions that can underlie a set of behavior. So as an example, and I'll show an example of why that's the case in the end. Also, once you have a reward function, it's difficult to evaluate how good that reward function is. If you haven't estimated the reward, you can't just evaluate it under you don't have a way to evaluate it. One way that people typically evaluate it is by solving for the optimal policy under that reward function, and then evaluating how much rollouts from that policy look like the expert rollouts. But doing this requires solving for the optimal policy. It requires running forward reinforcement learning with respect to your reward function. And that's incredibly expensive. And we don't want to do that every time we want to evaluate how good our reward estimate is. And lastly, the demonstrations may not be optimal. And if you make the assumption that they are optimal, then you'll probably run into some trouble. And in terms of the first challenge, an example of why demonstrations are underdefined, or why finding the reward function is underdefined, consider this example right here. There's a red triangle, a purple triangle, and a green circle. And say you saw this trajectory of the green circle moving along the trajectory of the gray line. So in this example, the reward function could be many things. The reward function could be to move away from the red triangle. It could be to move towards the purple triangle, or it could just be to move right. And there's this inherent ambiguity of which of those three, or which combination of those three, was the true reward function. Question? You could also use this to learn a more shaped reward function if you have a set of demonstrations available. Yes. Question? In practice, the trajectories should be at least close to optimal. There has been work on learning from both successful and failed demonstrations. But in general, it needs to be, it is possible to do slightly better than the expert, but not that much. Okay, so the algorithm that I'm going to focus on largely in this lecture is called maximum entropy inverse reinforcement learning. And it's quite a popular algorithm. It's one of the most popular algorithms for inverse RL. And the way that it handles this ambiguity of which reward function is the right reward function is by using a probabilistic model of behavior. Before I go into some of the details, I want to introduce some notation. So first, I'm going to define a trajectory as tau to represent a sequence of states and actions, S and A. I'm going to use R to represent the reward function, which is going to be parameterized by psi. And I'm going to use a capital R as shorthand to denote the reward of the entire trajectory, where the reward is just summed over time. And lastly, I'm going to use this large D to represent the set of expert demonstrations that are drawn from the expert policy. Okay, so what the maxent formulation says is that we're going to assume that the probability of a trajectory under the expert is going to be exponential in the reward. So what this says is that the trajectories that with maximal reward are going to be the most likely to be sampled from our expert, and trajectories that have lower reward are going to be exponentially less likely under our reward function. And then when we try to infer the reward function, what we're going to do is we're just going to do max likelihood. We're going to maximize the log likelihood of our set of demonstrations with respect to the parameters of our reward function. For those of you who are familiar with EBMs, this is simply an energy-based model for behavior. Where this gets a bit tricky is the partition function, Z, right here. Z is an integral over all possible trajectories of the exponential of the reward. And so if you're in low-dimensional state spaces, this is fine. And if you know the dynamics, this is fine. But if you're in high-dimensional state and action spaces, or you don't know the dynamics, gets extremely tricky to evaluate. And this is where the trickiness comes in generally in inverse RL. Okay, so how do we actually optimize a reward function? So this is our objective, the log probability. And we can then plug in our formula for the probability of a trajectory, the 1 over z exponential of the reward function. And then we can then break up this product into two terms. One takes the right term, the log of the exponential of the reward is just the reward of the trajectory. And then the first term, the log of 1 over z, becomes the negative log of z. And here I'm going to use m to represent the number of demonstration trajectories. Then after that, we can replace z with the sum over all possible trajectories of the exponential of the reward. I'm also going to switch the integral to a sum here and assume that we're in a discrete state and action space. Okay, so this is kind of what our objective comes out to. And what we're going to do to optimize this objective is we're just going to use gradient descent. And in particular, this is what the gradient is going to look like. So the left-hand side is just the gradient of the reward, the sum over your demonstrations of the gradient of the reward function with respect to the parameters. And the right term comes out to look like this. So because of the log of the sum, you need to use the chain rule to get the 1 over the inside of the log, which is the sum of the exponential of the reward. And then the right-hand side is applying the chain rule to the inside. Okay, so this is the form of the gradient. How are we actually going to evaluate this? So let's look a little bit closer at this right-hand term. This right-hand term is a sum over all possible trajectories. So we want to be able to simplify that so we don't have to enumerate all possible trajectories and evaluate this term right here. So what we're going to do is you can see that if you bring the 1 over x of the reward function to the inside of the sum, you get the exponential of the reward divided by the sum over the exponential of the reward. And that's exactly how we defined the probability of a trajectory given a reward function. The probability of a trajectory under the demonstration policy given the reward function. And we can simplify this even further by saying, instead of summing over all possible trajectories, this is equal to the sum over all possible states of the probability of visiting a state given the parameters of your reward function times the derivative of the reward function with respect to the parameters. Okay. Next, how do we get this, this P of S? So this is what's called your state visitation frequencies. This is the probability of visiting state S at any given point in time under the demonstration policy for a reward function parameterized by psi. So there's a dynamic programming algorithm for doing this. I'm going to go over that algorithm really quickly on the board, if there's chalk. Yep. And I'll try to write big so that the people in the back can see. So the goal is to get P of S given our reward parameters, our state visitation frequencies. And I'm going to use mu t of S to represent the probability of visiting state S at time t. I should erase this. So just from that definition, you can probably imagine what the dynamic programming algorithm is going to look like. So we can start by saying that mu at our first time set of S is just going to be the probability of our initial state equaling S. This is just our initial state distribution in the MDP. And then for all future time steps, equals 1 to t, mu, we can figure out what the next, the state visitation frequency at time t plus 1 is going to be. So what this is going to be for state S prime is going to be a sum over all possible actions times, and a sum over all possible states of the state visitation frequency of the previous state times the probability of taking an action given that previous state times the probability of reaching state S prime given state S and state A. So you iterate over all possible time steps, and this gets you the state visitation frequency for time t plus 1 for state S prime, which is basically just the state visitation frequency of, for all possible previous states and previous actions, the visitation frequency of state S times the probability of taking action A from state S times the probability of reaching state S prime given state S and action A. And then once you have pi or mu t, at state S, we can then define the probability of the state visitation frequency for state S, given your parameters, as simply being the sum over all possible t of mu t of S. So one thing to note here is that this pi here needs to be the optimal policy with respect to your reward function, because we're trying to find the state visitation frequencies under that optimal policy. So in order to compute these state visitation frequencies, we need to first compute the optimal policy, and then we're going to compute using this algorithm. Yes? No. No. So backset assumes that the probability of trajectory is going to be exponential in the reward function. So the highest, it'll have the action that leads to the highest reward in the long term will have the highest probability under the demonstration policy. But with lower probabilities, it will take suboptimal actions. And pi here, pi of A given S, is a probability distribution here. Question, yeah. It will, it has to come out to 1 because it is, so I guess I don't want to mathematically go through and show that it has to be less than -1, or less than 1, less than or equal to 1, but yeah, so this is, oh yeah, I think it should be an average. Yeah, it should be 1 over capital T, assuming that you're at every time step equally often. So I guess for completeness, assuming that you have a finite state, this should be 1 over T, where T is the length of the horizon of your MDP. Thanks for that. Okay. So that's how we get the state visitation frequencies that we're going to use in our gradient when we run gradient descent with respect to the reward function. So what does this look like as an algorithm? First, we're going to initialize the parameters of a reward function and gather a set of demonstrations. Second, we're going to solve for the optimal policy with respect to our reward function, and then use the optimal policy to solve for the state visitation frequencies P of S, which I derived on the board. Then once we have our state visitation frequencies, we can compute the gradient, which is written right there, and then update the parameters of our reward function using one step of gradient descent. And then repeat. And that's it. Note that you have to solve for the optimal policy within the inner loop of this reward optimization and solve for the state visitation frequencies. So this algorithm is really only applicable in settings where you know the reward function, or you know the dynamics, and you're in a low dimensional enough state space and action space in order to compute the optimal policy and compute the state visitation frequencies at every iteration. But one thing that I will note is that this doesn't make any, the original paper of Maxent IRL used a linear reward function, but the way that I wrote it out here is general to any nonlinear reward function. You just need to be able to compute the derivative of the reward function with respect to the parameters of the reward function. So you can use it, you can plug in a neural network reward function here, and everything will work out fine. Okay, so how can we scale this up to more complex problems? In particular, how can we handle unknown dynamics, and how can we avoid solving the MDP in the inner loop of the optimization? So here's the formulation. If we don't know our dynamics, we can't analytically compute our partition function Z. And so instead, what we're going to do is we're going to use samples to estimate our partition function. So if we're going to use samples, what distribution should we sample from? How should we sample in order to get a good estimate for Z? For importance sampling, to get the best estimate of this function, we want to sample from a distribution that is proportional, a distribution whose probabilities are proportional to the absolute value of the exponential of the reward function. Note that this is the optimal distribution, for the minimum variance solution for importance sampling for the distribution to sample from. And note that it relies on R, and we don't know the true reward function. So it's going to be hard to just pick a distribution to sample from and sample from that. So what we're going to do is we're going to adaptively sample to estimate Z. So instead, as we get a better estimate of a reward function, we're going to construct our sampling distribution that has that is proportional to the exponential of the reward function. And we're going to do this by constructing a policy, and we're going to then sample from that policy. So this is what we call the guided cost learning algorithm. The inputs are the initial policy and a set of human demonstrations. Then given the initial policy, you first generate samples from your policy. Then using their samples, you're going to update the reward function using the samples from your policy and using the set of demonstrations. The samples are going to be used to estimate the partition function, and the demonstrations are used to evaluate the first term in the gradient. Then once you have your estimate of the reward function, we're then going to update our policy using that reward function. In particular, as we update our policy, we're going to get a better distribution to sample from when we want to estimate our partition function for estimating the reward function. And then you iteratively run this procedure, get a better policy for estimating the partition function, and then as a result, get a better reward function for, get a better estimate of the reward function using the demonstrations. And then at the end of this optimization, you have a reward function R and a policy pi. The way that we're going to avoid solving the MDP in the inner loop of this problem is instead of fully optimizing the policy with respect to the reward function, we're only going to partially optimize. In particular, we're just going to take one policy optimization step in this process. So one way that you can see this algorithm is updating the reward function in the inner loop of policy optimization. It's also worth noting that there is a related paper by Jonathan Ho and Stefano Ermon at NIPS 2016 that has a very similar high-level structure. Some of the details are a little bit different. Okay, and then for those of you that are familiar with generative adversarial networks, you might notice that the policy here, the goal of the policy is to look like the demonstrations and to get high reward function. And this is analogous to what the goal of a generator in a generative adversarial network that's trying to generate data that looks like the demonstration data. And likewise, the goal of the reward function is to assign high reward to the demonstrations and low reward to the set of samples generated by the policy. And so this is analogous to the discriminator. So let's dig into that a little bit deeper. So generative adversarial networks were introduced by Ian Goodfellow in 2014. And similar to inverse RL, GANs learn an objective for generative modeling. And you can get some cool results like turning a horse into a zebra, generating faces, translating from edges to cats. These are some of the fun results. And the analogy between inverse RL and GANs is that in inverse RL, you're operating on trajectories, whereas in GANs, you're operating on samples, which are often images. In inverse RL, you have this policy that's generating trajectories, and in GANs, you have a generator, which is generating samples. In inverse RL, you have this reward function, whereas in GANs, you have a discriminator that is discriminating between data and samples. And lastly, I'm going to use P to denote the data distribution. Okay, so we can actually show a mathematical connection between inverse RL and GANs, which I'll quickly overview here. So first, let's look at the reward or discriminator optimization. So in guided cost learning, the discriminator has a bit of a special form because it's outputting this reward function. In particular, what the form is that you can first look at, this is the optimal discriminator that's outputting the probability that a trajectory came from the demonstration distribution rather than coming from the policy, the generator. Simply the ratio between the data distribution divided by the data distribution plus the policy distribution. In guided cost learning, the discriminator is going to take this form. So you just replace the data distribution by the Boltzmann distribution, the exponential of the reward function. And otherwise, if you take this form of discriminator, the optimization for the reward function in maxent IRL is the same as the optimization for a discriminator in GANs. In generative adversarial imitation learning, the paper by Jonathan Ho that I mentioned earlier, they use just some classifier to represent a discriminator, which is more akin to the standard discriminator that you see in GANs. And for both of them, like I said before, the loss for the discriminator is the same as the loss function for GANs, which is simply this cross-entropy loss right here. Okay, next let's look at the optimization, the objective for the policy or the generator. In GANs, the objective is this loss right here, which is trying to basically trick the discriminator into thinking that the sample came from the data. And you can show that this is exactly equal to this, which is first an entropy term, the expectation of Q of the log of Q, plus a constant minus the reward function, which is exactly entropy regularized reinforcement learning. It's just maximizing the expected reward and maximizing entropy. The other difference that's worth mentioning between GANs and inverse RL, the inverse RL procedure that I mentioned before, is that because we don't know the dynamics, we can't just backpropagate through our reward function into our policy. So in the unknown dynamics case, you can train your policy with reinforcement learning rather than just direct backpropagation. That said, I just gave a whole lecture on model-based reinforcement learning. One thing you can do is you can use a learned dynamics model to backprop through your reward function into your policy, and that was done in this recent paper by Baram et al. Okay, so this is the connection. Next, I'd like to show some experiments on running these inverse reinforcement learning algorithms. So first, I'll show the experiments for guided cost learning. I'll show, we ran a number of simulated experiments, but I think that the real world results are the most interesting and fun to watch. We looked at a displacement task where the state included the joint angles of the robot as well as the goal posed for the plate. And then we also looked at a task of pouring almonds from one cup to another, where the state did not include the goal position of the cup. It actually only included visual features that were learned with unsupervised learning, as well as the joint angles of the arm and the state of the arm. And then we compared to a method called relative entropy inverse reinforcement learning. And what this method does is, what both these methods do, is essentially instead of using the iterative procedure to generate a sampling distribution for estimating a partition function, they just pick some distribution to sample from and use samples from that distribution to estimate their partition function. So as a result, the partition function estimate can be quite off if the distribution isn't from a good distribution. Okay, so here are some videos. Here's a video of me collecting demonstrations on the PR2 robot, putting plates into a dish rack. We collected 20 demonstrations, and we didn't collect demonstrations for one of the positions, and that was the position that we used to evaluate the policy. Next, I'd like to show a video of the standard cost function that we use in algorithms like guided policy search, or the standard reward function that we use. I'll use reward function and cost function interchangeably. The cost function is just the negative of the reward function. This video, actually, I'll show it in a second, and it will fail. This isn't to say that we can't hand design a reward function for this task. We probably could, but it will require a lot of trial and error, and is a lot more difficult than just demonstrating how to do the task by hand. So here is the policy that I learned. It actually broke, I think, one plate during training, and it's quite aggressive because it's trying to get to the goal position as quickly as possible. And it actually also missed because the plate bent a little bit and it thought that it got to the right position. This is the result if you run relative entropy inverse reinforcement learning. Because it doesn't get a good estimate of the partition function, it isn't able to figure out how to do the task. And then here's the result if you run guided cost learning. So this is the policy that it learned for 2 different positions of putting the plate into the rack. And you can see that it learns to fairly gently manipulate the plate. Next, here are some demonstrations of me showing the robot how to pour from one cup into another cup. Here's the result of running relative entropy inverse RL. Again, because it didn't get a good estimate of the partition function, it isn't able to figure out how to successfully perform the task. Then here's the result of running guided cost learning. This is the policy that it learned at the end of inverse-RL. It's a bit close on this one. Okay, and then next I'd like to show the experiments from the Generative Adversarial Imitation Learning paper by Jonathan Ho. In this setting, the demonstrations, so all of these were in simulation, and the demonstrations were from a policy that was optimized by TRPO. And then they used TRPO as the policy optimizer. So in the guided cost learning experiments that I showed before, we used local linear models to optimize the policy, so essentially using guided policy search. And here are the quantitative results. So here, the orange lines are showing behavioral cloning, which is the method that I described before, where you just directly imitate actions. And the blue line is showing GAIL, is showing guided, generative adversarial imitation learning. In each of these graphs, the x-axis is the number of demonstrations that were used, and the y-axis is performance. And as you can see, using inverse reinforcement learning is able to more effectively learn from a very small number of demonstrations. In many of these examples, the number of demonstrations is on the order of 10. So that's one of the trade-offs between inverse-RL and direct imitation, is that inverse-RL typically requires fewer demonstrations because you're introducing more structure into the problem. One thing that's worth noting is that these plots don't show the number of samples that were used to optimize the policy. Because they were using trust region policy optimization, which is much more inefficient than guided policy search, it was using millions of samples just like regular trust region policy optimization. But if you use a more efficient policy optimizer like guided policy search, you can get much more efficient performance. Okay, and this is the conclusion that I mentioned before, that IRL requires fewer demonstrations. There's also some fun results. So there's a recent paper by Morel et al. That applied GAIL to data from human mocap. And they learned policies and simulation for human-like walking and falling and getting back up again. Okay, so some of the pros and cons of these two inverse-RL methods. The strengths are that they can handle unknown dynamics. Unlike the original maxent IRL formulation, they can scale to neural network cost functions or neural network reward functions. And if you use an efficient policy optimizer, you can scale, and they are efficient enough for real robots. Some of the limitations is that the adversarial imitation is notoriously hard. GANs are notoriously hard to train, although there have been more recent techniques that have made them more stable that I think would be quite exciting to apply to the inverse RL domain. Second, I haven't seen a convincing application of scaling these inverse RL methods to raw pixel observations, to raw images. Thus far, we've only been using mostly low-dimensional feature spaces. And lastly, the demonstrations are typically collected with kinesthetic teaching or teleoperation. So essentially just first-person demonstrations rather than just observing a person performing a task. Okay, to review, generally, I think one of the big takeaways here is that acquiring a reward function is important and challenging. And for reinforcement learning formalisms to work out, we need to first get a reward function. The goal of inverse RL is to infer the reward function given a set of demonstrations. One of the main challenges that comes up with inverse RL is evaluating the partition function. Initial approaches solve this by solving the MTP in the inner loop and or assuming known dynamics. And with unknown dynamics, we can estimate the partition function using samples. Lastly, I discussed the connection to generative adversarial networks, which shows that sampling-based maxent inverse RL is a GAN with a special form of discriminator and uses reinforcement learning to optimize the generator. Okay, I'd like to leave you with some suggested readings if you're interested in learning more. So two classic papers in inverse reinforcement learning. First is GAIL and Ng, which is a good introduction to inverse reinforcement learning. And then this 2008 paper is the maxent IRL paper that introduced the probabilistic model for inverse reinforcement learning. As for some more modern papers, this paper by Marcus Wolfmeyer showed how you can use maxent inverse RL using deep reward functions and known dynamics. Here is the guided cost learning paper that can handle unknown dynamics. And here is the generative adversarial imitation learning paper that uses GANs with inverse RL. If you're interested in digging a little bit deeper into some of the more advanced topics related to inverse IRL, here are some more papers. So here are Maxent-based papers. Here are adversarial IRL papers. There's also been work in handling multimodality. So instead of recording demonstrations for a single task, just giving demonstrations for many different tasks and having it figure out reward functions for those for the multimodal setting. And there's also been some work on handling domain shift, where the demonstrations that you get are not from the first-person point of view that the robot sees. Okay, with that, I'd be happy to take any questions. Thank you. Is there time for questions? Okay, there. Yes, so there is some recent work by Abhishek Gupta on learning just purely from observations rather than just like a video observation. Although he assumes that there isn't domain shift. And I think that there is, other than that paper, it's also being actively researched right now. But I don't have any other papers that come to mind. Yeah. Sorry, can you repeat your second question? Can you repeat your second question?
The maximum entropy formulation inverse RL that we went to. I was wondering if it could be converted to something, I'm not sure, but if it could be converted something like what to like divided into circular functions.
So you're asking if it can use both positive demonstrations and negative demonstrations? I haven't seen any work that has done that. One thing that I've tried informally is using negative demonstrations to evaluate the partition function. I haven't found significant benefit from doing something like that, but that is something that you could do to incorporate negative demonstrations, is use it as another sample to estimate the partition function. It's possible that there are other ways that you could do that as well. Yeah.
You showed a picture of chat boxes. What's the state of the art of IRL and natural language?
Yeah, I think there have been a few papers from Montreal and or McGill on looking at inverse RL for dialogue. So that's where I would look for that. One of the challenges is that in language you have discrete tokens, either words or letters that you're trying to generate. And GANs often have a lot of trouble with handling discrete tokens. So I think that people, that has been one of the main challenges, but I think that people have been trying to find ways to get around that. Yeah. Yeah, the ways that they're different is that first, that there's a special form of discriminator that we use that represents the reward function. I showed that form of the discriminator up on the slides. Another thing that I didn't mention is that in that form of the discriminator, we actually use the density of the generator. Because if we have a policy, if we have a distribution that's representing the probability of an action given a state, we actually know the density of, given an action in a state, we know the density of our generator and the distribution induced by our generator. So we can actually exploit that in our form of discriminator and use that when we optimize the discriminator, which we do. And the distribution, the trajectory distribution of the generator shows up in that equation. The other difference is that because we don't know the dynamics, we often use reinforcement learning to optimize the generator or the policy with respect to our reward function. Whereas in GANs, typically, instead of using reinforcement learning, you just backpropagate through your discriminator into the policy. Yeah?
In demonstrations, often it's like a multi-step. It doesn't work where, for example, if you've already know like the beginning step or how to approach the distract, but like now you want to make sure you go close to this. Is there like a attention mechanism or explainability as to, that's built into the inverse R so that you can actually see whether
I haven't seen attention mechanisms used with Adversarial. In terms of explainability, one thing that you can do is like take two trajectories and compare the reward function. And if like take an aggressive trajectory and a more gentle trajectory and see if it thinks that one of them has higher reward than the other. And that could show that that's one way to see if the robot knows whether or not aggressive or gentle is good according to its reward function. Yeah. I know that, so there's some work by Marc Toussaint on, the formulation in Marc Toussaint's work is that, say, you might know some constraints, like you don't want like object collisions, for example, and there's some work by his group on incorporating those constraints into inverse reinforcement learning so that when you learn your reward function, you also obey those constraints. So I'll hand it over to Marvin. Thanks.